Thank you very much. Okay, thanks. Hi, folks. I'm really happy to be here. This is my first time in Russia, so it's a big event for me. A big thank you for the organizers to having me today, because I'd like to talk about security, cryptography, encryption, and this kind of stuff. I'm working at a company where we're a little bit involved in Python, because our whole product, our whole stack is built with Python and Django for the front-end view part. So one of my job in this company is to put some advices and give some advices to our customers and our users about the data and the security. First fact is that users can't protect themselves. I mean, users don't have to know how to protect their data and don't have to know how to deal with their own security. I can't ask my grandmother, who is 85, to correctly protect her passwords, her access, use unique password in various websites and various services. So we have to do it for our users, because we can't trust our users to their data protection. Fact is, any sensitive data must be transferred or stored in an encrypted form. This is the only way to protect their own privacy and their own data. And this is our responsibility as product developers or architects or digital workers, to do some stuff to protect people and protect their data. So what do we need? We need cryptography. And this is the topic of this talk. What is cryptography? Cryptography is not about securing access, two-factor authentication, using passwords, and so on. Cryptography is basically just hash, encryption, key exchange, and signature. That's all. And the rest uses those primitives to secure the access and secure the data. So let's make a quick step back in history to understand the cryptography by itself and the encryption, to understand the flaws in it and how not to reproduce it in our everyday development. Fact is, cryptography is as old as war. I mean, for whole time, any people have wanted to protect their secrets from their enemies. So we relied on cryptography for a long, long time. And its brother, the cryptanalysis, which is the fact to try to decipher some text without having access to the key and the algorithm that protect the content, is as old as encryption by itself, because enemies always wanted to know the secrets. So this is our first problem and our first enemy. Let's see some flaws in encryption history to understand how not to reproduce them. First flaw is, I don't have the GIF, that's all. That's okay. First flaw is a too simple key. I mean, if your secret is protected with a too simple key, it's easy for your enemy to guess what the key is and to decipher the content. This is the first cipher, the first known cipher in the whole history. This is the shift cipher wheel, also known as the Caesar cipher. This is just basically two wheels. You just shift one along the other one, and the number of pads that you use is the key, and this is just a substitution, which is in this combination. I use 3 pads, and in my text, in my plain text, the A become a D in the cipher 1, B become a E, C become a F, and so on. Simple, efficient, and used for many, many years by the Roman and by Julius Caesar. It's efficient, yeah, but you just have 25 combinations in the Latin alphabet because you just have 26 letters, and in the 26th one, A stay A, so it's not really secured at all. So, fact is, you have to make the secret complex to guess to your enemies, because if you just have 25 combinations, it's pretty easy to guess and to decipher. So how to fix it? You have to use long length keys, and you have to make them hard to forge. So second problem is repetitions. In a polysubstitution algorithm, monosubstitution, algorithm, like the Caesar cipher, the letter stay the same one when you encrypt a whole content. So you will have a problem. You will have a problem because if you want to encrypt a complex text, even in the ciphered version, you will be able to count the number of letters, and you will be able to guess which letter is substituted. Some example, I'm French, and in French, the most used letter is the E. So if I count in my ciphered text the number of occurrences of letter, probably the letters that come the most often in my ciphered text is probably a E. If I'm able to guess this one, and if I'm able to guess 4 or 5 letters, I will be able to guess the whole key and to decipher the entire content. So I have to stick to another algorithm, and the good one is a polysubstitution algorithm. This is a Wigner cipher. Wigner cipher is basically 26 shift ciphers with one padding at all. And here's how it works. Let's say I want to encrypt the text attack at dawn. And I want to encrypt it using the key lemon. First thing is to pad my key to have the same length as the text I want to cipher. So I will pad my content. Then I will encrypt the A using the L key. Regarding to my matrix, I will get a L. If I want to encrypt the T with the E, I would get an X. But if I want to encrypt the T with the M, I will get an F, and so on. So the same letter do not remain the same one in the ciphertext regarding of the key used to do the encryption. It is pretty robust, and you can't apply frequency analysis by counting letters on a polysubstitution algorithm. Wigner cipher were strong for something like 4 centuries before it was cracked. And it was cracked using frequency analysis coupled with other hard mathematical problems. So it's strong enough, and this is the algorithm, or the kind of algorithm, the polysubstitutions one, that are used in digital ciphers now. So it's pretty strong. Fact is, you have to avoid common denominator, because repetition leads to some leaks, and you have to protect your content from that. And you have to use unique keys, because if you use the same key multiple times, you will probably have some kind of repetition that will conduct to apply some kind of frequency analysis, and so on. Third flow is the brute force attack. This is Enigma. Enigma is a cryptographic machine that was used during the World War II by the Germans to encrypt their communication between some part of their army. It is virtually unbreakable, even now, despite the fact this is just a mechanical machine. But, spoiler, it was cracked, otherwise this talk will probably be in German. So, this is how it happens. During the war, where you are on the battlefield, the operators weren't able to find a unique key to use each time. So they tend to reproduce some pattern and to use and reuse some keys. So it led to some kind of repetitions in their text and their communications. Their allies were able to decrypt the content due to 2 facts. The first one is that the plans of the machines leaked from the Germany to the allies. So the allies were able to understand how the machine worked. The second one was that they were able to build some super calculators thanks to Alan Turing, and those super calculators, bombs, were able to apply at a huge frequency, the frequency analysis, and they were able to decrypt the content. The only one they weren't able to decrypt was the Navy one. Why? Because they were using a kind of books that present the keys to use each day for a month. The only time they were able to break it was to sink a submarine, dive in it before the submarine were completely sunk, and go outside with the book, the code book, for just 1 month. This is a brute force attack. That's all, definitely. So keep in mind that no pattern is strong enough to resist to an endless attack. Your security will be forced at some point, and you have to be prepared to that. So this is a main flows, let's say, in cryptography. Let's go nowadays and see how to use it in your everyday. First part is about hashing, salting, and some kind of cooking. Hashing is about obfuscation of the data. You've got some plain data, you pass it through some kind of algorithm, cipher algorithm, and you've got an encrypted content. But you can go way down to go back to the plain text version. This is not possible just because the algorithm wasn't built to do that. This is the checksum algorithm we commonly use, like MD5 or SHA or whatever ones. Problem is, if you want to encrypt some kind of data to protect it, like when you want to do some kind of password comparison, if you want to use it and just talk to the checksum algorithm, you've got something on internet that is called the rainbow tables. And the rainbow tables are big tables, big data, where you will be able to find the checksums that correspond to a plain text version. So if you just encrypt your user password using the MD5 algorithm or the SHA-1 algorithm, this is just a big fail. Why? Because you just have to compare the checksum in some kind of rainbow table, and you will get the plain text version easily. So you have to make it complex to guess. This is done using the salt. So what is salting? Salting is adding some kind of entropy in your cryptography algorithm, and it will avoid repetition, and it must be unique and completely random. You add it to your password. So a good solution to do that is, I want to encrypt a password in my database, a user password. So I've got a new user that is signing in my platform, and I want to store the password in an encrypted form, so a hashed form. So I will first import the secret module that is easy to generate some kind of random content, and I will generate a random salt with some kind of random bytes. Then I will import the Argon2 algorithm, which is the strongest probably you can find nowadays to make some kind of checksum and hashing on your content. And I will initialize it using the hash secret row method. I will pass the salt. I pass the password by itself, and some kind of parameters, some kind of the number of the memory cores, the parallelism, the number of rounds you have to execute on your algorithm to make it stronger, and so on. This is just internal cooking. Then I want to save the hashed password in my database, so I have to compute a record. This record have the Argon2 name, because this is the algorithm I'm using. So if I want to update my process next time and change my algorithm, I'm always compatible, retro-compatible with my previous stored password, because I always known which algorithm is used for this password specifically in my database. I pass the salt that I have to save, which is same length each time, so it's easy to guess in my final length. And I will pass the hash, which is the result of my computation. I also save the various parameters that I've used to compute the content of my hash, and I just join them using a random character. It's $, but you can be free to use whatever you want. When I want to compare with my user password, when my user comes back to my platform, it will give me my its password, and I will just apply the same recipe to the given password and compare just the checksums in my database. Okay, so I will be able to recompute the same one anytime, as many times as I want. But I still have a problem. My problem is my database may be corrupt. An attacker can come on my server, attack my database, or inject some content in my database, and inject a password that is computed using the same method. So I have to be sure that my database won't be altered when my user wants to submit a new password and I want to compare it. So I have to digitally sign the password, the record in my database. So I will use the hashlib library and the hashmac library, and I will make a signature using the hashmac algorithm, using a private server key, which is hosted on the server by itself, probably in a secured part of my server, inaccessible to some attacker. And I will sign my record using a digest algorithm, and I will simply save the record and the digest. And I save in my database both records and signature, because an attacker that want to inject some password substitution in my database can be able to recompute a digital signature. So I have first to compare the signature, then to compare the password by itself. This is a bit complex, so fortunately I'm going to come with a password hasher function which does exactly the same thing that the complex one that I did just before. But this is for the example, simply. Your record is just simply at that to compute. It will generate the salt by itself, the parameters, the record with the separators, and you just have to digitally sign it and save it in your database, and that's all. But if you want to do it by hand, that's the recipe. Fact is that a properly hashed password has no repetition and is executed in a time control environment. This is why I use the Argon2 algorithm. This is because it's pretty much slow, which is not a problem for my user, because I just had something like 300 milliseconds. So this is nothing when you want to log into a platform. But if you attacker have to brute force your platform and want to try many passwords, adding 300 milliseconds to each try is a big amount of time at the end. So you have to make it complex and difficult to perform on your platform. So it decreases the risk of a brute force hacking. This is about hashing. What about key encryption and key-based encryption? First thing is how encryption works. It's based on math, simply. It just relies on complex math problems to perform some kind of substitution, like we did with cipher wheel or with the Wiener algorithm, but in a digital form. There is two kinds of family in key encryption. First one is block ciphers. It takes a big part of data, split it in some blocks with the same length, and apply substitution in each block. The substitution is done with a dedicated algorithm, but the manner that the blocks are chained together is part of another kind of algorithm in the digital world. The most common, or the first known, is the DES algorithm, the data encryption standard, but we will encounter it a lot of time. It's totally deprecated because it's pretty easy to crack. So you have to stuck to the IES or the IDEA, the blowfish algorithm. Basically, they took a block, make a substitution, and use the substitution to perform another kind of substitution with the next block, and so on. So this is the most common that you will probably encounter. The blowfish is probably the strongest one today. And there is a kind of operation in which way you will take a block in the chain to perform the substitution to the other one, and so on. Does it happen? Does it apply before the substitution, after the substitution? This is some kind of operation. This is a block mode operation. Same thing, the most common are the ECB or the CBC, but they are totally deprecated. Now we use probably more authenticated encryption, which means they're performing some substitution on the block and they sign the block in the same time to be sure that the content won't be altered during the substitution. All of them use big randomness to apply the substitution and to perform the substitution and make it repeatable. But problem is that our computers aren't truly random. So we have to perform some kind of randomness and some kind of initialization in your block mode algorithm. So we have to deal with padding and randomness. It means that you have to add to your algorithm some kind of initialization, which is the IV, the initialization vector, to initialize it in a state that is not able to be reproduced to perform the kind of substitution later. You have to use the CSP-RNG, which are cryptographically secure pseudo-random number generation functions. There are functions in our cryptographic libraries that are able to return true cryptographically random numbers, pure random numbers, because due to their designs, computers tend to reproduce some patterns in the CPUs and in their memories. So we have to find a way to avoid that. The CSP-RNG function are that. So please don't use your random direct access because they are not secured anymore. And you have to use some kind of initialization vectors. I don't want to go too deep inside this part because it's just crypto stuff and we're not here for that. But you have to know that they exist, and this is some parameters that you have to add to your block modes of operations when you want to deal with them. Second families is stream ciphers. Stream ciphers are some kind of ciphers that don't operate on blocks, but directly on a stream of data, which is pretty much badass, but is not really usable because the first known algorithm is the ERC4. It was involved in the WPA algorithm used in the Wi-Fi protection, but it was cracked because if you want to encrypt randomly a huge amount of data that is streamed to your algorithm, you have to make a random key along the content to be able to be padded to the rest of your stream. So it means that if you want to encrypt some kind of like 8 GB of stream, you have to generate an 8 GB key, which is really not acceptable. So you have to reproduce some part of the keys to keep it small in your memory, and reproduction tends to repetition. So it made finally C4 easy to crack. There are two kinds of algorithms probably able to replace the ERC4. There are the JJ20 and the Panama, but they are not really strong or considered as strong enough today. So WPA finally go back to block modes and to block ciphers. So streaming cipher will probably be able will probably be usable with quantum computing, but not with our everyday computers. So both of them use keys to encrypt and decrypt the data. But how to deal with keys? How to exchange a key to keep it solid and strong and resistant? First family is symmetric key ciphers. You've got an algorithm, you pass it your content and your key, it encrypts the data, and if you want to decrypt it, you pass it through the algorithm again using the same key, and you've got access to the plain text content. Cool, fast, really easy to use, and particularly adapted to a big amount of data. But a symmetric key must be shared with your recipient if you want to exchange some kind of data, which means the key could leak. And if your key leaks, it's a game over. So you have to protect the key by itself. There is a solution to exchange a key without never sharing the key itself. It's the Diffie-Hellman algorithm. So here, how it works. We have two people. This is an example using DNA. Woo! You have two people, and they want to exchange a secret. They want to exchange it and encrypt it, so they have to share a key. But they don't want to exchange the key to prevent some leak. So they have their own DNA, and they agree on a mutual shared secret, which is here, let's say, some kind of virus. This part is mixed with their own DNA, and they obtain on their both part a potion. This potion is a mix of their own DNA and the shared secret, which is some kind of virus. Then they exchange the potion. They mix the potion of the other part with their own DNA again, and boom, they've got the same result on the both parts. Trust me, it works. So they could use the same secret they have at the end as a symmetric key for their algorithm without never sharing it before, and just shared a shared public secret and having it mixed with their own DNA. It was imagined and created by Diffie and Hellman, which were two researchers in cryptography. And they did that because they were working on asymmetric cipher, a solution where you can use two keys, one to encrypt and one to decrypt. But they weren't able to find a correct algorithm to do that. So they finally found a solution that is a mix between having a secret and having a symmetric key that work. And this is a good solution because it's fast enough to apply in some kind of cryptographic content. It's easy to use and easy to implement, and it is used in our browser because the TLS, or previously the SSL algorithm that protects our HTTP secured connection, is definitely based on the Diffie-Hellman algorithm. Each time your browser wants to access an HTTP server, it just performs a request, and they use the Diffie-Hellman to exchange a unique temporary key to encrypt the content of the transmission for just a request. So it's strong enough if you want to temporarily exchange some part of data. If you want something more robust to exchange a big amount of data, you've got this asymmetric keys. In the asymmetric keys, you've got one private key. This private key is your own. You keep it and never share it with anyone. And you have one or more public keys that are derivated from that private key. The public key is used to perform some kind of encryption. So if someone wants to send me some content, it will use my public key, send me the content encrypted with my public key, which is easy to find because it's public. And I'm the only one able to decrypt it because I'm the only one to have the private key associated with the public key used for the encryption. And the private key is the only one able to decrypt. It's really efficient because you never share any kind of secret. You never share any private part. Even in the Diffie-Hellman, you shared some kind of potion with your own key inside it, so it's not safe enough. So asymmetric key is pretty strong, but it's also pretty slow. It doesn't fit well to a huge amount of data. So if you want to send some big part of data or to store a big amount of data, you can't rely just on asymmetric keys to do that. You have to use a mechanic that is called key wrapping. More on that next. About asymmetric keys, you've got two kinds of keys, the RSA and the elliptic curves. There are two standards. The RSA one is based on prime numbers. It's the first one known as asymmetric keys. The elliptic curves use the elliptic curve math problem to perform the keys. So it means that RSA, because it was the first one, is widely adopted, but ECC has smaller keys, smaller ciphertext, smaller signatures. So if you can, always stuck on ECC. But if you need a huge adoption context, prefer RSA. But SEC is pretty much available everywhere now, so use ECC. So what about if I want to encrypt a big amount of content, but I just have asymmetric keys, because I want it strongly protected? I will do some kind of key wrapping. So, first one, key wrapping is about packing contents together. I will first generate a token, which is a random string, and this random string, this token, will be used as a symmetric key. I will use a blowfish algorithm and generate the initialization vector and initialize the cipher. So I use a token, I use a CBC mode in this example, and I use my initialization vector. So I've got a cipher algorithm that is ready to encrypt my content. But I want to protect the symmetric key in my message to having it strongly protected when I want to transfer it. So I will use an asymmetric content. So I import the public key, the recipient public key in my method, and I will encrypt the token using the public key. So I've got a token, a symmetric key, ready to encrypt my content, and the symmetric key is encrypted with my recipient public key. Okay? So I will encrypt my message with some kind of padding content, which is cryptographic stuff, and adding the initialization vector and pack it with the encrypted token. So if you want to send or to store a big amount of message, a big amount of data, you encrypt it with a random symmetric key, and you encrypt the symmetric key with the public key of your recipient. This is the only way to really protect easily your content, because you have the better of both worlds. You have the fast of the symmetric algorithm and the strong protection of the asymmetric one. Okay, what about signature? Signature is always asymmetric cipher, but reversed in the other way, which means I will encrypt, let's say encrypt, not that, but let's say we encrypt the content with the private key, and we send it, and the public key is able to decrypt the content because it is a public key associated to the private key. It is not safe because anyone could be able to decrypt the content because the public key is public, but it ensures that the key used to sign the content is the private key associated to the public key. And because this is your private key and you are the only one to have it, it means that you are the original emitter of the message, of the content. So this is a way to ensure that the content comes from a correct person, a known person. This is a mechanism that is used in certificates. Let's say we want to have some kind of certificate authentication. What is a certificate? It's like a badge that is able to open a door, like your bedroom door. And this badge has a pair of key inside it, a public key and a private key associated to the certificate. And on the badge, you have your name, your photo, and some kind of other stuff. So it's like an ID card. It identifies you. And this card is emitted by a known, trusted authority. So when you want to access some results, you knock on the door of the server and you pass it your certificate. First thing is the agent will ask the authority if the certificate is still valid or not. If not, you are rejected. If yes, you can continue to the protocol. So the agent will use your public key in your certificate to encrypt some kind of challenge. He sends it to you. You decipher the challenge because you have access to it, because you got the private key associated to the public key used to encrypt the challenge, and you sign the challenge using your private key, and you send it back to the agent. So the agent will be able to compare both the challenge and the signature because he's got access to the public key. Okay? And if both challenge and signature match, then you've got access. Otherwise, you're not. Okay? Simply to say, yeah. Yeah. So, okay, but how to use it in your day-to-day? Let's dive in. If you want to protect some content, let's say, you have to protect some content. You have to protect your network. To do that, you have the TLS and the chain of trust of certificates. You want to protect some passwords. You've got the hashing functions and the hashing patterns. You want to protect data. You've got asymmetric cipher with key wrapping and probably some kind of HSM devices, which are devices that store and perform the encryption actions directly in a dedicated device plugged into your computer or your server. So the keys won't be able to any attacker. So if you develop with some low-level languages, you've got some access to some OS, your operating system modules, like in the Linux kernel. You've got access to some kind of low-level libraries like OpenSSL. You've got dedicated hardware to do that. But not everyone is doing some low-level languages. We are working with high-level languages. I'm formerly a front-end developer, so trust me, doing operating languages is just a pain in the ass. So when you work on desktop or the server, you can work with Python, of course, with the cryptography module or the PyCrypto library. Ruby, you've got NACL, Node.js, the crypto building module, and so on, each for each languages. But we've got a problem. Our problem is if each language implements their own library, it means they require a lot of effort to maintain all of them to a state of the art in kind of cryptography, and you have to make it strong enough to be sure to be reviewed to any other implementers. And cryptography world is a really small world. I mean, OpenSSL was sad to die 2 years ago because there are just 2 maintainers to OpenSSL, or at least 1 maintainer and 1 reviewer. So it's really complex, and we have to mutualize our effort, to share our effort on libraries. So maybe a good solution is a multi-platform library. And woo, we've got them. We've got 2 libraries. The first one is libsodium, and the other one is a library published by Cossack Lab, which is Themis. I use libsodium because it's an open source library. It's widely developed, widely adopted, written in C, but accessible to any other languages using some binders. So you can use it in any language that you want, even in C, even in Python, even in Node.js, even in JavaScript, even in your browser if you want. So it's probably one of the most useful library you can use. So let's say I want to encrypt some content for my client. I've got a client, and I ask for a specific content, and my server need to encrypt it before sending it back to my client. So on my server, I've got a root, which is /secret/something, and I will encrypt the message, never gonna give you up. And I want to return it in an encrypted form. First one, I will import the box class of my libsodium library using the libsodium binder available for Python. So in the back, it uses a C libsodium library, but it's totally abstracted in my Python code. I want to encrypt for my user specifically. So when my user asks for the content, it passes in my root its username. So I'm able to use my user model to get access to the user data and to access to its public key, which is stored in my server. It's public, it's okay, it's safe. I pass the public key to my box. But libsodium requires that you also pass the server private key to initialize the box. So I will also read my private key that is stored on my server, and I will pass it to my box. So I've got a box ready to encrypt some content. The box is initialized using my server private key and my user public key. So I want to encrypt the message. I will encrypt it and using the box encrypt method, but the box encrypt method requires a nonce to be initialized, that is some kind of salt. So I let the user define a nonce and pass it to the method directly when it calls the endpoint. So I simply call from my client the secret/username/nonce, and I will simply encrypt the message using the libsodium box method and return the encrypted result. That's all. You don't have to deal with which kind of block mod algorithm, which kind of substitution algorithm you want to use. You don't have to deal with that. libsodium makes the choices for you. If you want to dive in it and tweak it, you can. But if you're not a cryptographer, and you're probably not, then you just have to stick with the default parameters offered by the libsodium library, and it's strong enough. Trust the cryptographer behind it. So, okay, but it's for desktop, server, some kind of clients, but if I want to use it in a mobile or a web environment, because more and more of our applications are web-based and based on web technologies, and using cryptography in your browser is probably something complicated, because JavaScript is not secured enough. You can use the WebCrypto browser API, but it's harsh. It's a tool dedicated for cryptographer, conceived by cryptographers. It's totally unusable for day-to-day use. So you have to rely on high-level library. I've got this conference. I gave it for the past 6 years. And 6 years ago, I said, the day we will have a library like jQuery, but for the cryptography, it will be a big win. We've got it. It's libsodium, accessible directly in your browser, thanks to WebAssembly, because the C code of the libsodium library is compiled to WebAssembly to be executed in the browser. So let's say I want to access the previous endpoint directly from my JavaScript code in my browser or in my hybrid application embed in some web view in my mobile phone or something like that. I will call using a fetch, I will call the secret/username endpoint. So I will get in return the encrypted form of my message, which is the response text version. I will initialize my libsodium library using a libsodium wrapper. It will load the WebAssembly module directly in my browser, instantiate it, and make it ready to execute some kind of operations. So I can simply use CryptoBox Open Easy, which is in the name easy. using the server public key, and which is publicly available, blah, 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 and my user secret key, my private key, which is stored in my application, in my mobile phone, in my browser, wherever you want. I will pass to it the encrypted format that I've got from my fetch call. But remember, we need nonce, so we will rely on libsodium by itself to generate the nonce, pass it to the fetch call, and pass it to the CryptoBox OpenEasy method, and I've got access to the message. Easy, nothing to tweak, nothing to understand about the low-level access to the library. It just worked. Easy, but what about authentication? Our authentication are mainly based on password nowadays, but we all know that passwords are probably not the best way to protect users and protect their access to some kind of part of our platform. So we need probably a public key cryptography, which is based on a passwordless authentication, and that will use a public-private key algorithm to perform some kind of challenges. This is exactly what web authentication standard stands for. You've got 3 parts. The first one is the registry part. Your client will access to your server and say, OK, I'm a new client, I need an access, and I want to register. The server will say, OK, generate a new pair of key and send me your public key. So the client will generate the pair of key, will send the public key to the server, and the server will register, store it in the database, the public key. Then it will send the registration result to the client. When the client wants to authenticate, it will ask the server and say, OK, I'm ready, I want to authenticate. So the server will generate a challenge. This challenge is encrypted using the public key of the client, which is stored in the server database. And during the login, the client will just test the challenge, decrypt the challenge, sign it, return it to the server part, and the server will authenticate it or not to give it access to the restricted part of the platform. This is exactly the same mechanism that is used in the certificates. Exactly the same one. But wrapped and embedded in a dedicated standard usable with every kind of client and every kind of backend languages to your web access and web platform. I made an experiment a long time ago, but I'm a little bit short of time, so I will show it to you later if you want. But let's say it's fine. This is just certificate authentication. So, conclusion: you have to think cryptographically. This is the only way to protect your users and protect your data and protect their privacy. And this is your responsibility. Never try to be a sorcerer apprentice. Never try to make your own cryptographic algorithm, your own recipes. It never works. It's a job for mathematicians and cryptographers. I'm not nor a mathematician nor a cryptographer, and you're probably not. If you are, that's cool, and you can contribute to those kind of libraries. But otherwise, do not try to invent new things. Stick to the standards and trust the existing cryptographers and the libraries. Never forget that security has an inverse relation to the ease of use. The most robust and the most protected is your platform, the less usable it will be. So it's just a cursor you have to adjust for your users and for the security that you want to provide them. And it's security as a cost. This is my final slide. It's a post that came from Redis 5 or 6 years ago during the Ashley Madison leaks. Ashley Madison is a platform dedicated to dating in the United States. It's pretty much used. This is the biggest one in the United States. And this guy said, okay, I was in the United States for my studies. I'm gay. And I used the Ashley Madison platform to meet some people because it was easy. But nowadays, the Ashley Madison database leaked. And I'm back in my country, which is Arabic Saudi, and the homosexuality is punished by death. So I'm scared for my life. I don't think that the Ashley Madison developers thought that they probably put their customers' life in danger by not protecting correctly their privacy data that the users give them during their process. But they did. So it's your responsibility to protect your users' data and privacy as developers. That's all for me. I'm Mads. Like I said, I'm a tech evangelist at Always Data. We're a PaaS provider, and we're working on facilitating hosting and giving access to a more robust and more trusted web. So we are involved in some kind of security, and one of the main part of my job is to educate and give some advices on how to use it and how to use it well. If you've got some questions, we've got something like 5 to 10 minutes, so it's fine. If you're totally dead, I can understand too. But yes, sir, we've got a question.
And you should choose 2 questions for the prizes.
Okay, so thanks for the talk. I've got a question. What's the best practice today for storing private keys on our production servers?
Okay, storing private keys. The best solution is probably HSM, which are hardware secure modules. There are some kind of, they could be big servers, or they could be just some kind of USB dongles like this one. And this is some kind of dongles where you can store your private keys. They are not accessible from the file system. And when you have to perform some kind of operation with the private keys, you just ask the HSM module to perform the operation, and the HSM module returns the result. So there is no more private key actions done on the server by itself, and the key can't be stolen in case of compromission of the server. It's probably the best solution. It was not affordable before, but thanks to some initiatives like NitroKey, the HSM module are now accessible for something like $30 or something like that. So it's really easy to use and easy to understand. So don't hesitate to plug one in the back of your server. Another question? And yes, sir.
Okay, thank you for your slides. And my question is, as I understand, the one of most important parts of the key generation is the true random generator. But I see that you used special libraries, new examples which are used to generate keys. But are they use the true random generator? So this is still like a regular.
So randomness. There is 2 kinds of randomness. There is true random devices, which are plugged in USB in your server, but they use some kind of unpredictable environment to produce random generators like temperature, hygrometry, pressure. So they are really not affordable. They cost a lot, and not everyone could be able to have this kind of devices. But the cryptographically secure pseudo-number random generators are functions that are dedicated to generate some kind of pure cryptographically numbers by using the random generator of your system, like the urandom in the Linux kernel, but apply some kind of derivations on it to ensure that there are no repetition in them. So do not use urandom directly, but use the cryptographically secure functions in the libraries, in the cryptographic libraries, because they are able to perform some kind of truly random numbers in the context of a cryptographic environment. They are not really random, but they are random enough for cryptography.
Thank you for your report. As you mentioned, the other side of cryptography is convenience for users. So, does it work?
Yeah.
Well, so if you make an ideal cryptographic system, if somehow you forgot the key, you will lose your data forever. Do you know a lot of legal companies who really prefer to pay that cost for security, to lose all their production data, all their data which means their business, for only security reason?
Do I know a company that is ready to do that? Okay. Tempered answer. Maybe, maybe not. This is exactly what Nextcloud do with their end-to-end encryption protocol. Nextcloud is a private cloud system. You can install it by yourself to store your own data. This is some kind of drive, private drive that you can use. And they have a cryptographic module that allow you to do some kind of end-to-end encryption. So you store, what you store in your drive is totally encrypted and unable to be deciphered on the server side. Just the client will be able to do it. So if you lost the key, you lost everything. But Nextcloud is not the company, it's just the company that produces the software. This is, the data is not their value. So this is your choice to activate the end-to-end encryption. This is your choice to probably lost everything if you lost your key. So a company that is ready to do that, I don't think so. Because if your company rely on data to produce some value, you need the data. So you have to probably change your mind and find another way to bring some kind of value without using your users' data to protect it a lot. But once again, this is an adjustment between security and usability.
So actually, this is just to follow up to that question that occurred to me. It seems to me that the right answer is an N of M shared secret algorithm.
Yeah.
But you can probably explain that better than I can. Well, I mean, anyway, you're on stage. But what I don't know at all is, are there any good libraries for working with that, especially with Python bindings? Or N of M shared secrets?
Yeah. Yeah. No, I guess. Yeah, in Python, I guess Lipsodium is probably able to perform some kind of enemy shared secret exchange, but yeah, you probably have to stick to low-level libraries like OpenSSL and so on. So using it directly with Python is probably not that easy. But there are some kind of binders, not that well maintained. Maybe this is the next effort for the community to bring a new library with a good abstraction level to be able to access to this kind of primitives. Yeah.
Hi. So I want to ask, like, are there any threats or attacks that exist for a cryptographic system?
Sorry, excuse me.
Are there any threats or attacks that exist for a cryptographic system?
Some kind of attacks for the crypto that targeted the cryptographic system. Yeah, there's a lot. Yeah, you will have to. There's, I guess, some kind of attacks that try to access ciphered database and try to decipher them. That try to brute force attacks, that try to guess access to private keys or to trusted certificates to control the rest of the chain, because in the certificates architecture, you've got a trusted authority that delivers certificates, and those certificates can be used by clients to authenticate, but they also can be used to authenticate other certificates, and this is a chain of trust. So if you control the root of the pyramid, you control everything in the trusted chain of certificates. So this is some kind of attacks. Yeah, there is a lot, and you can protect yourself for everything. So you have to guess what is your threat model, and what is probably dangerous for you and your business and your application, and try to find some way to avoid it. But you can't protect yourself to anything.
Thanks a lot. It was
Thank you.
interesting. I have a little provocative question. In your opinion, can the rapid development of quantum technologies be a threat to all modern cryptography in principle? Thank you.
Quantum technologies is probably the next technology, the next era of cryptography, because using quantum technologies, you're able to break even the asymmetric algorithm, because using quantum technology, it's easy to compute huge prime numbers or elliptic curves. So, fact is, current quantum computers aren't able to do that, but the algorithm to do this already exists. We just have to have the technology to run them. So when the quantum technology will be sufficiently affordable to everyone, even the asymmetric technology with the asymmetric keys won't be enough to protect your data. So you will have to find another solution, and the other solution will probably come from a quantum cryptography, which will be able to perform some kind of cryptographic operation that the quantum computers themselves can't be able to break. But this is for the next time. There is some kind of implementation, some kind of experimentations, but nothing really for production nowadays. So you can stick to asymmetric keys for now, but be prepared to change them in the next probably 10 years or less.
And we have time only for the one final question.
It's not even a question, but a small remark. There you, in some place, use user.pk,
yeah,
right? And pk like public key,
yeah.
Yes, yeah. But in web development, it's that abbreviation is easy to misunderstand with like primary key, and so maybe it will be better to open it.
Of course, I guess I did
avoid misunderstanding.
Yeah, thank you. I guess I did that for the first time because I want to shrink my content to be able to fit in the screen. But yeah, you're true. PK is probably to avoid. But keep in mind that those terms of P key and S key is often used in cryptographic world. So we have to manage some kind of mixed content between public key or primary key. But yeah, naming is hard, you know. Okay, thank you very much. Thank you for your time.
Thank you. And